So welcome guys, we're going to start talking about chemistry as it relates to the topic of biology. But before we can really get into the basics of biochemistry, we really kind of need to step back and do a refresher of some basic chemistry concepts. So first off, if we're talking about anything that takes up space, has mass, we're talking about matter. And at the end of the day, whether it's biology, chemistry, physics, everything we're dealing with is matter. So matter may be atoms, elements, compounds, and how that all kind of fits together. Something I want to just point out, just to remind you, so we define matter as anything that occupies space and has mass, but remember that mass doesn't necessarily equal weight. Right? So when we're measuring mass here on Earth in a lab, we're talking things in units of grams, kilograms, that sort of thing, right? But truly, mass is the amount of material that's in an object. So when I'm measuring mass in grams or kilograms, we often use those same units for weight, but remember, weight is based on gravity. So if I were to measure a penny here on Earth, alright, its mass and weight, value and unit would be the same, but I go and take that penny to Jupiter or to Mars or to the moon, and its mass won't change because the amount of material isn't going to change. It's inherent to that penny, but its weight will change because the gravity that's pushing down on that object will be different. Same thing with you. Your mass will never change no matter where I stick you in the universe. But let's just say that you're 150 pounds here on Earth. Well, you're going to weigh a little less on the moon because there's less gravity. I'm going to throw you on Jupiter, which has got even more gravity than Earth, and you're going to weigh even more. So just keep that concept in mind. Alright? So if we're talking matter, then these are sort of your three big vocab terms. We've got atoms, we've got elements, we've got compounds. And an atom is the smallest particle of an element. If I break down that atom any smaller, which I can do, there are things that make up atoms, there are smaller pieces. But that atom will no longer retain the properties of that element anymore if I break it down any smaller than that. It's the same thing with a cell. Right? A cell is the smallest unit of a living thing. While it's got smaller components to it, it doesn't fit those characteristics of life anymore. Your elements, these are your pure substances. Alright, and a pure substance is something that cannot be broken down into any other substance via chemical means or physical, once again, without losing its inherent characteristics. Alright, so physically I can smash an atom together and get particles, but it will not retain those particular characteristics that are inherent to that element or to that atom once I break it down any further. For us, we spend a lot of time talking about compounds, so now I'm taking those elements, putting them together in different ratios, and chemically combining them. So a chemical reaction has to happen, energy has to get put in order to put those elements together, combine them in some sort of fixed ratio, and that's where I get those compounds from. Alright? So keep those vocab terms in mind. So here's what I mean between pure substance versus a mixture. So a pure substance, we're talking elements and compounds, always has the exact same composition regardless of where I take it from, the exact same properties. So if I take something like hydrogen out of the atmosphere or out of a sample in the ocean, hydrogen is hydrogen is hydrogen. It's going to have the same reactivity, the same flammability, the same atomic structure, the same properties. Same thing if I were to go to the sun or another planet and take hydrogen from there, it's the exact same thing. Alright, compounds, same deal. If I take water vapor out of the atmosphere, out of the ocean, go to Venus and take water, go to Mars' polar ice caps and take water. Water is H2O no matter where I get it from. 2 hydrogens, 1 oxygen, and chemically it will always function the same way. The opposite to that then are these mixtures, and these are where I'm going to mix different substances together. They're sharing the same space, but they are not necessarily chemically connected to each other, and so they may or may not retain the same properties regardless of where I take them. Think of something like sand. Alright, sand is a mixture of different minerals, different rock pieces, and I can be on the exact same beach and take 20 different samples of sand and get slightly different compositions, which may react slightly differently because of those different compositions, regardless of where I take it. And I may only be within a 2 or 3 foot radius of my starting point. So there's your big difference. For now, we're going to focus on the pure substances, so your elements and compounds. We'll talk about mixtures a little bit later on. So let's start with those atoms, right? So this is the smallest particle of an element, that so long as I keep it together, it's going to retain those properties of that element. That being said, it is made up of smaller particles. So when we look at an atom, you've got 2 major structural components, or spaces, that exist in an atom. You've got your nucleus in the center, and that's where we're going to house your protons and your neutrons, right? Protons have a positive charge. Remember, your neutrons are neutral, so no charge to them. And that's where most of the mass of an atom exists. These protons and neutrons are pretty large particles. So overall, the nucleus of your atom contains the majority of its mass, and its also overall net charge is positive, right? Positives from the protons, there's no charge from the neutrons, and so overall your nucleus is positively charged. Hanging around outside of that is your electrons. Alright, these are much, much, much smaller particles in terms of size, and they're also then negatively charged. So a little bit more background, right? So protons, positively charged subatomic particle. These guys are found in your nucleus. If we start assigning charges to atoms, for every proton that exists in that nucleus, that atom has a positive 1 or plus 1 charge. Alright, so if I look at the picture here in the diagram, this particular atom has 3 protons, so it would have a 3 plus charge. In order for an atom to exist, period, I have to have at least 1 proton. I can literally exist as an atom with a single proton, no neutrons, no electrons, and I'm still technically, by definition, an atom. And that happens a lot to hydrogen. Alright, but generally speaking, most other elements, most other atoms are going to have some neutrons, some electrons hanging out there too. Alright, but the only requirement really is a single proton. Something else to keep in mind is that each atom or each element has a unique number of protons. So, here's a mantra for you to say before you go to bed every night. If you change the number of protons, then you're changing the element. Alright, so if you change the number of protons, you've changed the element. If I change the number of protons from hydrogen, which has 1, to helium, which now has 2, they are 2 different elements. Okay, so keep that in mind. I can change the number of neutrons, I can change the number of electrons without changing the element, but if I change the number of protons, I now am talking about a different element. Speaking of neutrons, so these guys are the other particle we find in your nucleus. Has almost the same mass of that of a proton, so remember I said most of your mass of an atom is hanging out here in the nucleus. This is the biggest, most massive part of that atomic structure. But remember, these guys are neutral, right? So neutral means there is no charge, positive or negative, doesn't matter, there isn't a charge to these guys at all. That being said, if I change the number of protons, right, remember I changed the element, but if I change the number of neutrons in an atom, I still retain that element, but now I've got something called an isotope, and that's what you see down here along the bottom. So if I take a look at isotopes, I'm dealing all with carbon, right? So 6 of my protons, alright, in every single atom down here. But notice that this number changes. So carbon 12, 6 protons, 6 neutrons. Carbon 13 is another isotope of carbon. Still 6 protons, which is what makes it carbon, but now I've got 7 neutrons. Do the math, 6 plus 7 gives you 13, that's where that number comes from. Carbon 14, same deal, 6 protons, which is still why it remains carbon, but I now have 8 of these neutrons. 6 plus 8 gives me the 14. And what ends up happening is the more neutrons that I pack into that nucleus, the less stable it remains because it's getting heavier. Alright, and so a lot of times we'll see these different isotopes, especially when they get to a certain level or a certain number of neutrons, they get heavy enough to become radioactive. And we're going to talk a little bit about radioactivity in some other contexts moving forward. Alright, your electrons, these are your negatively charged particles, and these guys are found outside your nucleus. Alright, just like every proton I have has a positive 1 charge that it adds to that atom, your electrons have a negative 1 charge that they add, alright, because they are negatively charged. So, if I'm talking about an overall neutral atom, then my number of positives or protons has to be the same as my number of electrons. So if I take a look at this particular diagram here, I've got 3 positives, right? And I've got 3 negatives to cancel them out. Alright, so overall, this particular atom is neutral. If I start changing the number of electrons, then we start getting into things called ions, and we'll talk about that when we get to ionic bonds in a little later. Before I leave the electrons behind, there's something I wanted to point out. So we know that these electrons exist in this space outside the nucleus, right? So here's my nucleus. Electrons are hanging out on the outside of that. That being said, the way in which we describe where those electrons are found is a little different depending on what our ultimate question is, what our line of study is, what our purpose for discussing those electrons are. So I've got really 3 basic models that can describe where an electron exists, and some of these models are more helpful than others depending on what my purpose is for describing where those electrons are. So we can talk about them being in energy levels. So how much energy does that particular electron have given its location near the nucleus? I can talk about it as an electron cloud, and this is just a visual model saying somewhere outside of the nucleus at this particular radius, those electrons have to exist. Or I can talk about them as orbitals, which is probably how you've learned them in the past, and we're talking about these sort of rings in which we would most likely find those electrons. For us, in terms of diagramming out electrons, talking about how many there are, where they're arranged, we're going to spend most of the time talking either energy levels or orbitals. The electron cloud, technically probably the most accurate, because we're just saying this is likely to be where those electrons are. But in terms of really studying atomic structure, not necessarily as useful. Alright, so we'll stick to energy levels or orbitals, and I'll give you a couple analogies in just a second. Something else to remember is where those electrons are going to want to place themselves, or where they're most likely to be found. and that's the idea of that electron configuration, right? So when I look at that first orbital, okay, or first energy level, the one closest to your nucleus, remember that one's always going to hold up to 2 electrons. We move out from there, second, third, so on. Those orbitals can all hold up to 8 electrons. So when we're talking about electron configuration, remember we always fill from the nucleus out. Alright, that's the most stable electron configuration an atom can have. So in this particular situation, I've got 3 electrons, so I'm going to fill up my first orbital with those 2, and then that third remaining electron is going to end up in that next orbital out. So let's throw some analogies at these different models that I can use to describe where electrons exist. Energy levels are going to be something that we're going to talk about, especially when we get to things like photosynthesis. So an energy level, think of it like a staircase. The landing of each step is the energy level itself. So the higher I go up on the steps, the more energy that's associated with that particular step. If you remember anything about potential energy, right? The higher you are, the more potential you have in terms of energy, because the further from the center of Earth you are. So if I'm starting all the way down here at the bottom of the staircase, there's my ground state. That's orbital 1 or energy level 1. And that ground state, for those electrons, they have the lowest amount of energy that they need to have in order to maintain their distance from the nucleus, right? If I go up a level, I'm now going to have to increase my distance a little bit, increase the energy that I need to stay in orbit. Same thing here. A little bit more energy because I've got a slightly bigger orbit to maintain. So every time I go up a stair, I'm increasing the energy that it takes to get there. Alright? Think of it like having a basketball in the middle of the football field, right? And so I've got one student who is circling that basketball, and they are a meter out from the basketball, right? I throw another student out 2 meters from that basketball, but they need to maintain the same orbit or the same rate as the person at 1 meter. What does that mean? Well, that person at 1 meter may be able to walk a really nice, slow, casual pace, but that means the person out at 2 meters is going to have to move a little bit faster to stay in orbit and stay at 2 meters from that basketball. I go 3 meters, same deal, they're going to have to move a little bit faster, have a little bit more energy. Well, that's kind of what's happening with your electrons. The further out you get, the more energy they're going to need to be having associated with them. They're going to have to move a little faster to maintain that orbit. Okay? Now here's the other thing. If those electrons get moved out of their ground state, they're going to move by stairs, right, or move by energy levels. And we talk about those electrons being then in an excited state. So let's just say I gave this particular kid who's going 1 meter around candy bars, okay? And let's assume this kid is, I don't know, a 3 or 4-year-old. What's going to happen? Well, they're going to all of a sudden go on a sugar high. So they're going to be able to start spinning around that basketball way faster. Well, we're not going to keep them down here because they can only maintain that slow, casual pace around that basketball in that ground state. So let's say instead, now they've got enough energy to be up here and still maintain that same rotation around that basketball. They're now in an excited state. Now, just like that kid on that sugar high, those electrons in that excited state will eventually find themselves unstable because they'll start losing energy as they come off that sugar high, right? And so they'll crash back down to ground state. And we'll talk more about what happens to that energy when they move between energy levels, because it's going to be really important for how plants are able to actually harvest light energy from the sun and convert it into sugars that we then can eat and use as consumers. Electron cloud, windmill's a great example or an analogy for this, right? So when we talk electron cloud, we're talking about the fact that those electrons have to exist somewhere in this particular radial space, right? Within this circle, we know those electrons exist. But at any given point in time, there's no way to know exactly where those electrons are in that particular moment. Same thing with a windmill, right? We know there's, say, 15 blades going around, but if it's spinning fast enough, it's really difficult to be able to locate any particular blade at any particular moment in time. Alright, so similar idea. Your orbitals, alright, these are regions within that radius that we know those electrons are most likely to be at any point in time. So we can use a map, let's just say, of the school. And for a week, you're going to take that map and you're going to put a dot on that map once every 10 minutes for that week. Alright? Those dots then become your orbitals, or at least an analogy for them. They describe the most likely locations for where we're going to find you. So if I'm looking at your map at the end of the week, where am I going to see the highest concentrations of dots? Probably your classrooms, the cafeteria, places where you spend a lot of time, right? Places where you don't spend crazy amounts of time within those 10 minutes, the hallways, hopefully the restroom, right? Those are sort of those spaces between orbitals then. Okay, so we're simply saying that statistically, electrons are most likely to be found in these particular regions within that radius because of where they would typically spend the most amount of time, and that gets associated with things like their energy and things like that. Okay, so atoms are the smallest units of an element, right? Elements are on your periodic table. We'll walk through how to read that again, how to use that, but we're talking about chemistry in relation to biological systems. So for us, there's about 25 elements on the periodic table that are essential to life functioning. Alright? And of those 25 elements, in fact, there's only 4 of them that make up 96% of living things, and that's where we're talking oxygen, carbon, hydrogen, and nitrogen. The other 21 elements that are important to life, we talk about them as trace elements. Okay? Now, that doesn't mean that trace elements aren't important. It's just that they don't make up crazy amounts of matter in living things. Alright? You're going to be responsible for having to know 6 total elements in relation to how they associate with living organisms. The carbon, the oxygen, the nitrogen, and the hydrogen, as well as 2 of the trace elements, your phosphorus and your sulfur. Okay? Before we move on, though, here's a point about those trace elements. Iodine, not necessarily one you're going to have to memorize in terms of chemical structure, but iodine is a trace element. Okay? So a lot of kids say, oh, trace element, not really important, right? Well, not so much, right? So iodine in and of itself, you only need approximately 0.15 milligrams of iodine in your diet each day, which is virtually nothing, or at least it sounds like nothing, right? But why do you need it? Well, if you don't get it, you end up with something called this goiter, right, or this sort of growth. If you've ever seen anybody with an Adam's apple, think about that, but bigger. Okay, not the same thing as an Adam's apple, but structurally, if you were to look at somebody, it would look similar. And iodine deficiencies, about 90% of the time, result in these goiters. What are they? Well, you've got this gland that sits right behind your neck here, alright? And when your thyroid gland doesn't get enough iodine, it can't produce these two hormones that it needs to help you function, alright? And these guys are responsible for everything from hunger and weight maintenance and all kinds of things. So what ends up happening is that because that thyroid can't produce those hormones without that iodine, you get these buildup of other chemicals and other molecules, and you get this big, enlarged, swollen thyroid gland, and that's what's pushing out, and that's where that goiter comes from. Generally, for most people, harmless condition, alright, although it may cause them to cough a little more, may make it a little more difficult to swallow or breathe. Not something that's crazy common here in developed countries, because we get so much iodine in iodinized salt, right? And think of all the things that have salt in them. Your potato chips, we use it to cook all the time. So most of us get plenty of iodine. This isn't an issue. But take a look at the salt containers at the grocery store the next time you're there, and you can see that there's iodinized salt versus non-iodinized salt. So salt that has iodine associated with it and salt that doesn't. And it's a really easy additive that we can add to that salt that we can then ship to places that are more sort of third world countries where this is a bigger issue because they're not getting it naturally in their diet. And we can have them add this to their daily routine in terms of cooking. And for most people, so long as that goiter isn't really big, we get that iodine back in their diet, and we can get that goiter to kind of shrink back down. So, while it's a trace element, and you don't need much of it, trace element doesn't necessarily mean that it's not important. So just keep that in mind.